14.3. Today we're going to do double integrals in polar coordinates. Do you remember this problem? It involved a lot of nasty algebra that I left to you to do. And after you did the nasty algebra, then you had to do a trig substitution. The problem really was a bear. I would like to do the problem again, only this time I would like to use polar coordinates. Do you remember the conversion from Cartesian to polar coordinates? I have the equations boxed in for you. Rewrite the integral using polar coordinates. I'd also like you to rewrite the region. This is what I get. The question now is, what is dA? Remember, dA was the base of each box, and the base of each box was a rectangle. Well, we have a polar rectangle now, so this question is trickier than you might think at first. I'm going to leave the theory for another video. In this video, my only goal is to show you how to integrate using polar coordinates. Here's the trick. When doing a double integral in polar coordinates, insert the factor r. So dA is equal to r dr d theta. You need r in order to get a true polar rectangle. Also, you're going to want to integrate first with respect to r and then theta. So here is our integral. Once we have the integral written, it's not too difficult to integrate and evaluate. I pulled out the 2 and I distributed the r, and then I went ahead and integrated, and then I evaluated, and I end up with an integral in terms of theta, which I then integrated and evaluated. Find the volume of the region beneath this surface and above the annular region. So this time, instead of our region being bounded by a circle, it's a region in between two circles. So r is varying from 2 to 4. The region has already been given to us, so we don't need to figure that out. However, we want to write z as a function of r and theta, and again, use the conversion from Cartesian to polar. And this is what we get for z written in terms of r and theta. We are now ready to set up the double integral. And check your work. Did you forget the r? Always insert the r when switching to polar coordinates. Always. There's no exceptions. And then remember it's dr and then d theta. So set the bounds up appropriately. We're now ready to integrate and evaluate. First, I distribute r. Then I integrate with respect to r. Remember to keep theta fixed. Next, I use the double angle formula. And then I integrate and evaluate. Polar coordinates simplify some problems considerably, such as the first one we did. If you find yourself doing a trig substitution or your region is circular, ask yourself if the problem isn't easier in polar. After we do triple integrals in the next section, we will come back to this arena when we study cylindrical and spherical coordinates.